I want to welcome you to another apply regression analysis class. Of course, the focus today will be on shrinkage methods. Earlier in the week, I think I introduced us to regularization. I introduced us to how we can actually handle variable selection in regression modeling. And of course, I remember I talk about uh, method of shrinkage. I talk about all subset selection. I also talk about the stepwise regression. So the main focus today will be on shrinkage. We want to see how shrinkage work. Of course, we've already seen how all subset selection and how the stepwise regression work. We identify the weak point as well as the strength, and of course, we want to we want to also explore alternative method. So, once again, I welcome you to method of shrinkage. In the outline, of course, the bottom line, we've been trying to see how we can improve on the ordinary least square. Of course, I told you the other time, the performance of the ordinary least square can actually be in jeopardy when the numbers of features in regression modeling is more than the number of observations. We expect the OLS, to perform badly in that regard. And what can we do to improve on the OLS? And one of the one of the ways out is through shrinkage. And that is why today we're going to focus on shrinkage. We want to understand the shrinkage method, uh, and we also want to see if there exists or any limitation. We also want to take the advantage of the strength. So because we normally have issue with bias and variance, I'm actually going to, explain what is the connection of bias and variance in this. And of course, lastly, I'm going to spend my time on the method of shrinkage. They also call the method of regularization. Okay, that will call the ridge regression, the lasso regression, and of course, or the combination of the two, because we can also have the combination of ridge and lasso regression that we call elastic net. So I'm actually going to walk us through, uh, what is the situation where we need to apply any of that. Okay, so once again, we want to improve on ordinary least square, and of course, we've identified three ways to do that. Of course, I've walked you through the all subset selection. I've walked you through stepwise regression. Of course, I believe I will also explain dimensionality reduction technique that we call the principal component analysis, but the main focus today will be on shrinkage. Okay, now let me tell you this. We don't just do what we do. There's a reason why we do what we do. Okay, why do we need shrinkage? What is the problem that we likely have for us to consider, regularization approach, or to consider shrinking the regression parameter towards zero? Of course, because we want to perform variable selection, and not only that, we probably want to solve a problem, maybe caused by maybe problem of overfeeding or underfeeding. Okay. But how am I going to know there's overfeeding? How am I going to know there's underfeeding? I first want to explain the concept of bias and variance. Now, I wanted to take a look at this. Okay, 1 second. I wanted to take a look at this particular image. Okay. Now, what do we mean by bias? What do we mean by variance? I need you to pay attention. Okay, so that you can see the connection, or you can see, distinction between them. When I say bias, you know, it means the error arises in the model as a result of model specification. When you misspecify your model, okay, when you misspecify your model, if your model is not being specified correctly, of course, you're going to have issue with bias. And and that is why I said the other time, the worst enemy of everyone in scientific community is bias. That is their worst enemy. They are very, very careful, when they want to specify their model. Of course, a physicist, an economist, a statistician, we start model, building by specifying a model. They use principle of subjectivism. Okay, you know, they specify their model according to their belief. Okay, their belief that the model they are specifying is actually going to work, and uh, there's a way they can investigate whether the model is right or not, and that is why every model have assumptions. Okay, now the variance, on the other hand, if for instance I fit different um maybe different training models and my model behave differently. I'm going to say that again. If I fit model for different subsets of training data, okay, and my model has high sensitivity, okay, then that very model has high variance. Okay, the variance is caused, okay, by if there's a small change in your data and your model reacts significantly. Okay, I'm actually going to call that high variance. Now, we don't want high variance, we don't want high bias. Okay, now let me tell you this. We cannot eat our cake and have it. A statistician may want to correct because they are always after reducing bias, and they try to increase the number of variables in the model, because believing that when I add more variables into my model, I'll be able to solve the problem of bias. Even though they are able to solve the problem of bias, but you know what? They're creating another problem of high variance, because the moment you have a lot of variables in your model, your model will be noisy. Your model will be complicated. Maybe your model is going to be more complicated than reality. Let me say this. We want a situation whereby we want to fit appropriate model for given reality. We don't want a situation where our model will be too simple. If your model is too simple, your model is not going to detect the pattern. Your model is not going to depict the underlying trend. Okay, if your model is too simple. And if your model is too complicated, okay, your model will memorize the noise. We don't want our model to be too simple. We don't want our model to be too complicated. We want to be in the middle because of that. Now take a look. Now that you understand what I mean by bias and the variance. Now, since we cannot actually minimize the two at the same time. We can't, but we want an ideal, reasonable situation, or where we will be able to strike a balance between the bias and the bias and the variance. If you take a look at this guy here, what you see at the center is like, I want to eat something. Maybe people are like some shooter, maybe soldiers, they are trying to aim at a target. Okay, the target is in the middle. Okay, now when you take a look at this now, even though they are not able to aim at the target exactly, but what they at the end of the day, they what they actually where their stuff land is not far away from the target, and there's a little variation, then I'm going to call that low bias and low variance. Low bias and low variance, an ideal situation. Take a look at this. This is low bias and high variance. This is like a statistician that make his or her model to be highly complicated, maybe probably to reduce bias. He or she has succeeded in reducing bias, but he has created a new problem of over parameterization that we call the high variance. And when they say, when your model has high variance, your model will overfit. Overfitting means your model will perform excellently on training data, but will perform poorly on the unseen data. Why is it going to perform poorly on the unseen data? Because your model has memorized noise as well. Okay, your model memorize the training data, and your model also memorize noise. That doesn't make sense. Okay, now there's a situation where we have high bias and low variance. A statistician doesn't like this kind of model, a model with high bias, you know. So you can see all the blue, they are clustered. Clustered means there's a little variation, but this is far away from the target. Because it's far away from the target, then we're going to say this is high bias. That's not good at all. But you know what? This is a double tragedy where you have high bias and high variance. You can see the blue, dotted point, they are scattered away, indicating the spread out. There's more spread out, indicating high bias, and at the same time, none of them is kind of close to the target. We don't want that. Okay, now here I think I just gave you the meaning of low bias, high bias, you know, and so on like that. I remember in statistical theory, you know, when you talk about an estimator, we expect on average, we expect an estimator, okay, we expect expected value, if the expected value of an estimator equal to the true value of a parameter, we normally say the estimator is unbiased. Okay, now what I mean by low bias, since let me tell you this, it may be typically, or let me just say, impossible to eradicate bias. This is just theoretical that, oh, okay, and that was why we normally say on average. We're not saying the estimator is the same thing as bias or as a true parameter. We're not saying that, but we're trying to say average, on average, estimator is the same as parameter. And that's why when I say parameter, I mean the target value. So that was why I said the average prediction very close to the target value. That's for the low bias. If I talk about high bias, then I'm actually going to say the prediction actually differs significantly from the actual value. Okay. And of course, I think I've given you what the low variance and the high variance actually talk about, when you use different maybe subset of training data, and your model reacts significantly to different set of training data, okay, which means your model has high sensitivity. Of course, That's going to be high variance. And of course, for us to be able to make a good model, okay, we need to strike a balance between bias and variance. Now, the way to achieve that, the way to strike a balance between bias and variance is actually to go by way of a shrinkage, by way of a regularization. So it means initially, the conventional linear regression model that we have does not incorporate regularization parameter. And what we want to do by regularization is actually to include a restriction on the model to include what I'm actually going to call a regularization parameter that we actually strike a balance between the bias and the variance. Okay, so and that's why here I said the regularization is actually one of the way to improve our model. We do not only want our model to work well with the observed data, we also want our model to work well with unseen data. We want a very good generalization. Okay, and we believe that we can achieve that through regularization. Okay, and that was why I said, the regularization minimizes the validation loss. Okay, and trying to improve the accuracy of the model. And let me tell you this, the only way the model can actually avoid overfitting is through regularization. That's exactly what I mean. And the regularization would mean that, okay, you know what we're going to do? Can we have a way, if I have so many predators, can we have a way to shrink, the regression coefficient associated with some irrelevant predators towards zero? I'm going to say that again. The regularization, we enforce what I call sparsity into the model, shrinking, the regression coefficient that correspond to irrelevant or maybe predator with a weaker, very weak relationship towards zero. To be able to do that, like I said, we shrink. Shrinking means you are actually forcing, the regression coefficient associated with irrelevant predator towards zero. It's either you shrink it to zero or you shrink it towards zero. Okay, now let me tell you this, and that is what I'm trying to explain here. When you are able to shrink it to zero, then you or towards zero, you're actually reducing the variance. But let me tell you this: when you reduce the variance, this approach reduce the variance. But if you're not so careful, you're actually going to fabricate high bias, increased bias. But the sparsity parameter or the regularization parameter should be uh, data driven. It should be the one that you should compute from data so that your shrinkage parameter will actually strike a balance. You are not going to choose a shrinkage parameter, that we only reduce the variance and increase the bias. You don't want that. Okay, and that's why, computing your regularization parameter will be data driven. You know what? Under regularization or shrinkage, we got two methods. Number one is a lasso. Number two is the range. I'm going to tell you the difference between the two. When I'm applying lasso penalty, lasso will shrink the regression coefficient of irrelevant predator to zero. It will completely eliminate them. And because of that, I'm actually going to say lasso perform variable selection. But there's going to be an issue with lasso situation where predators are they highly correlate. For instance, if I have predator X1, X2, and X3 that correlate. Lasso we drop one, we retain only one of them and drop the others. And when Lasso drop the other, okay, uh, and they are correlated, then your model will become unstable. So Lasso is not a good choice in a situation where you actually want to keep a group effect. You want to you want to maintain group effect. Okay, so you don't need Lasso. But if you want to perform what I call variable selection, okay, where you are guided, you know the variables that play a key role, and you know those ones that are nuisance, of course, go with Lasso. And provided they do not correlate, go with Lasso. But the ridge, on the other hand, will not shrink them to zero exactly, but it's going to shrink them towards zero, and it's still going to retain them in the model. They're still going to be in the model, except that they're no longer going to be significant, but they're still going to be in the model. And when they are in the model, then it means if they are correlated, then it means Lasso can handle correlated predictor variable. And I'm also going to say this because of this property, the range can actually handle multicollinearity. I'm going to say that again. You know, Lasso will shrink the regression coefficient of your relevant variable towards zero, but not exactly zero. Let me say this. Lasso will shrink them to zero completely. Ridge will shrink them towards zero. Lasso will completely eliminate them from a model, but Ridge will not eliminate them. Okay, if the Ridge is not going to eliminate them, even though they are in the model, they are not going to be significant. Now, take a look at this. Well, two of them, whether Lasso or Ridge, they are about striking a balance. They actually want to stand they want to strike a balance between bias and the variance in a way. They want to have a low bias at the same time with a low variance. That is the intention of the two. Okay, so the Lasso regression use L1 penalty, and the Ridge regression use L2 penalty. Now let's go into the model. Let me tell you this. Pay attention. If you take a look at this guy, oh, 1 second. If you take a look at this guy, this is the residual sum of square of the ordinary least square model, okay, that we're trying to minimize, okay? But if there's a problem in a situation where we may specify a model, or there's a lot of variables in the model, we are not going to minimize this guy only. What we're going to do, we're going to add this is a Ridge parameter. Okay, if you take a look at this now, this is the Ridge, the whole of this is what we call the Ridge penalty that we're bringing in. The lambda itself is a tuning parameter. If lambda is zero, okay, then we are back at the ROSS. We are back at the conventional or residual sum of square for the ordinary least square. Take a look at this. Okay, so when we're increasing lambda, okay, then it's actually going to penalize more predictor variable. Okay, and that's why I said the larger lambda, the more the shrinkage. Okay, so this is a Ridge penalty. Okay, if you take a look at that, that's what we call Ridge penalty. Okay, now if we want to perform the optimization, we also need to control what we added. Then we're going to introduce what I call a constraint, where we're going to say the summation of beta j square have to be less or equal to a particular value. Otherwise, that guy is going to be too large. We want to restrict it to the maximum value that is going to have. It's actually going to be S. So this is Ridge. One more time, I told you what Ridge does. Okay, the Ridge use L2 penalty. The Ridge is actually going to shrink the regression coefficient or corresponding to irrelevant predator towards zero, but not necessarily zero. We're still gonna have them in our model, except that they are no longer going to be significant. But you know what? Because we are still having them in our model, REGRESSION does not perform a variable selection. But REGRESSION is good. REGRESSION can undo multicollinearity well. Okay. Now, this is what I just talked about. Okay, and this is particularly useful when the number of observation is less than the numbers of features, or we have outliers in our data set, or predators are highly correlated. We need REGRESSION in that regard. Okay, and of course, you know, now let's go into the computational advantages of regression. Of course, REGRESSION actually has an edge over the subset selection that we did the other time. The all subset selection, we have to go through all modules. That's computationally uh, expensive. So REGRESSION is better than that. With REGRESSION regression, we're not going through all modules. Okay? So because when the numbers of predator is increasing, the numbers of modules to consider in all subset selection will increase exponentially. But the range, of course, is going to make sense. And let me also tell you this. Range is also very, very useful. Of course, I mentioned the other time situation where your predators are are correlated. Okay. And of course, when the number of features is greater than n. Okay. Now, let me tell you this. This is the conventional OLS, and this is the range. Do you know what we're bringing in? Lambda high. High is an identity. Lambda is the turning parameter. Does that make sense? If you take a look at that. And let me tell you this. Do you know there are situations where there exists extreme or severe case of multicollinearity? The OLS is going to break down. Do you know that? When the number of features is more than the number of observation, we expect the ordinary least square to break down. Don't forget, the ordinary least square actually rely on there's something that we call central limit theorem in statistics and the law of large number. We expect situation where your sample size is large. But what of in a situation where your sample size is less than the number of features? We call that situation high dimensional data. Okay. We expect ordinary least square to to fail with high dimensional data. And that's why REGRESSION is actually going to come in to address that. I want to go into LASSO. Why do I need LASSO? Because a REGRESSION does not perform a variable selection. REGRESSION is going to shrink the regression coefficient corresponding to the relevant predator towards zero, but not necessarily zero. It's going to retain them in the model. But if we want to perform variable selection, we need LASSO. Because what LASSO is going to, let me tell you this. Another thing I failed to mention, because REGRESSION is still going to retain all the variables in the model, that can create interpretation issue. And the only way, one of the way to get out of that problem is to sparse your model. Sparsing, because your model was too dense. There is high density in the model. Okay. Then what we need to do is you want to completely eliminate. And if you want to do that, you're going to use LASSO. And that's what I said here. Okay. You take a look at that. Okay. So that's what I said here. Now let's take a look at the the statistical architecture. This guy is the residual sum of squared when I'm only focusing on the OLS. This is when I added the reach penalty, And that's why the all of that is RSS plus the reach penalty. But what about lasso? In a lasso, okay, this is the conventional RSS. Then this is the lasso penalty. Okay, what is the difference between the reach penalty and the lasso penalty? One involve a square, the other one involve the absolute value. That is the difference. Okay, if you take a look at the two. And of course, also under a lasso penalty, we're actually going to consider what I call constraint optimization, where we expect the sum of the absolute value of the beta j to be less or equal to s. Okay, now why does the penalty matter? Of course, you all know why the penalty actually matter. Why do I need to apply lasso penalty? Why do I need to apply the reach penalty? Of course, I need a lasso penalty if I actually want my model to be sparse. I don't want an interpretation issue. I want few numbers of predators in my model. Then I need lasso. But what if in a situation where I actually want to tolerate as many as possible numbers of parameters, I mean numbers of the predators in my model. Okay, maybe a situation where there's multicollinearity, and I actually want to handle multicollinearity. Rich regression is one of the best technique in statistics to handle the problem of multicollinearity. Okay, now, like I said, the lasso use L1 penalty, the ridge use L2 penalty. Okay, I think I've explained that. Okay, let me tell you this. When the lambda, whether you're talking about ridge or you're talking about lasso, okay, the similarity they have is that there's a turning parameter lambda. Okay, so when the turning parameter lambda equal to 0, okay, that means there is no bias. Okay, lambda equal to 0, no bias. Okay, and when lambda is equal to infinity, lambda equal to infinity means I want to consider maybe the highly sufficient values of lambda. Of course, there's not going to be variance. I mean, there will be no variance. But let me tell you this: we can never achieve that. That's why we need to use a data-driven approach that we can have a way to figure out the values of lambda optimally. Okay, now I said something here. Can we say whether ridge or lasso is better? It depends on the situation. It depends on your intention. And I'm going to say this. If your intention is to make prediction, I'm going to say this again. If your ambition is towards prediction, you need ridge. Because to make a better prediction, you need so many variables in your model. But if your intention is explanation, okay, interpretation, then you need lasso. Does that make sense? Okay, I'm not going to say one is better. It depends on the situation. This is what I'm saying. This is what distinguishes between them: predictability and interpretability. If you want better interpretability, okay, go with lasso. If you want, improve predictive performance, go with reach. And of course, we have a way to select lambda. We can use the method of cross-validation. And of course, with the method of cross-validation, uh, we actually going to choose the lambda value that correspond to the minimal cross-validation error. So we got a threshold. But let me tell you this. Is there any question before moving forward? Because of the disadvantage of reach and the disadvantage of lasso, lasso struggle with correlated variable. Reach actually could make our model to be noisy because um, it's still going to retain all the features in the model. But can we have a way to combine the two penary where we'll be able to perform the job of variable selection, and at the same time, we're actually going to retain some most significant variables in the model? And the answer is yes. And that is what we call elastic net. Elastic net, we combine L1 and L2 penalty. We're going to have both the reach penalty. And that's why, take a look at this. This is the residual sum of square from the OLS. This is adding the lasso penalty. This is adding the reach. Okay. Now, just like what I said, I think I've been able to highlight the limitations of reach and lasso. And of course, I said, when variable selection is your goal, go with lasso. If interpretation or model explanation is your goal, go with lasso. But if your goal is predictive performance, go with reach. But if you want to strike a balance between the two, you actually want to have a form of, predictive performance and at the same time interpretability properly, go with elasticness. We have a way to investigate. Because of that, pay attention. I want to walk you through a code, our code of doing this. I'm going to cite a scenario, and I'm actually going to compare the performance of OLS with reach and with lasso. I'm going to say that again. Maybe in your practical assignment, maybe what you want to do, you want to look into comparative analysis of OLS, ridge regression, and lasso. But for you to be able to know the one that will do a great job, it is better you know what you want. You pretend to know what you want. You now want to subject the three models to detect the true. You already know the true. So which means you need to artificially fabricate your data. Take a look. This is the code. You know what I'm doing? Please pay attention. Take a look at this. Uh, this is my code. Okay. That code involves lambda. Don't forget I need lambda, the tonic parameter. Okay. I want to code for range now. Okay. And you have to set a seed for reproducibility. Okay. Now, if we all set the same seed, we are going to have the same results. Now, I want to simulate a scenario where I have 500 observations and 10 features. But you know what? I know what I'm looking for. That is my true regression parameter. I'm simulating a model, okay? And I already know my regression parameter. I know number one is 0.5, number two is negative 0.5, number three is 0.25, and I know the four of them is 0, 0, 0. I already know them. But I want to test the performance of the conventional OLS, the reach, and the lasso. Does that make sense? That is the way that's what we do in research. Before we start applying to real life data, we artificially fabricate data set and we already know the truth. Now, at the end of the day, here I'm assuming lambda equal to 0.1. Take a look at what I have. This is the true values that I already know. Oh my God. Using the OLS, this is what OLS is going to give me. But you can see here, no agreement with the OLS. Okay, very close. No agreement. Okay, very close. If you take a look at that. Okay, and if you take a look at this, when we apply reach, this is what I told you. Reach will retain all the features in the model. So take a look at that. Okay, reach look to be very close to the true value if you compare them on a pairwise basis. Then I did the same for the lasso. Okay, you're going to get surprised now. If this is a true relationship, you have 0, 0 part of that. You're going to see what Lasso is going to give right now. This is the code for Lasso. Keep going. The same thing. Oh my God. Look at the Lasso. Look at here. In the true relationship 0, 0, 0, Lasso was able to reproduce that. Can you see that? So, but let me tell you this, if you really want to know, you know, which one is the best, apart from matching the regression coefficient, the true regression coefficient, we have a threshold. We have a metric of evaluation that we can use. And do you know the metric? Can somebody remind me of the metric of evaluation we're going to use here? If I want to compare OLS with Ridge with Lasso, we've done it. We did it this week. Go ahead. Thank you so much. Which means, generally speaking, you're going to use a metric of evaluation that has to do with model fitness and model complexity. The AIC, the BIC, and the adjusted R square. Does that make sense? And we can also, if we are working towards prediction, there's something that we also call root mean square error as well. Okay, now, I think I just give you a fabricated data set. Let's talk about real life. Take a look at this. I'm looking at the effect of all these variables, okay, on the response. Okay, I need to load all these packages. Okay, now I have 574 observation. With that, you know what I'm going to do? I will need to partition my data into two. I'm going to have training set and I'm going to have a test set. Why am I partitioning my data into two? Oh my God. Because I don't want to artificially fabricate relationship. This is a real data set. How am I going to know for me to be able to know the performance of my model in my entire data set? I'm actually going to split them into two. One is going to be for training, or the majority of that will be for training, and the rest is going to be for test. Does that make sense? You know why I partition my data set? Okay, that's what I'm doing here. Okay, if you 0.7 me, I want to commit 70% to training. Then I'm going to commit 30% to test. You have to set a seed. This is if I want to know the dimension in the train and that. Okay. Now, this is the code. Okay. And I fit linear regression. Don't forget, I want to fit OLS. Fitting OLS, this is what I'm going to get. Okay. After getting this, then I need a metric of evaluation. I want to get the adjusted R squared. Okay. And at the same time, I also want to get the root mean square error. Take a look at this. You know, uh, if you take a look at what I have here, okay, I'm actually talking about, I'm going to get the adjusted R square for training and adjusted R square for test. The root mean square error for training, the root mean square error for test. That is why you have these four values. And this is the interpretation. For the root mean square error, okay, is 0.94 for training, 1.1 for test. That is for the root mean square error. Okay, for the R square, I think adjusted R square give us the same for both training, and the test. Okay, please pay attention. This is for the OLS. Okay, this is for the OLS. Now, I want to use a regularization now, where I want to use the reach. Take a look at that. This is the code for the reach. When I'm done with the code for the reach, and I find the root mean square error, all of that. Now, this is, if you take a look at what I have right now, okay, this is for the training, this is for the test. If you compare this, the root mean square error here, okay, for both training and the test, if you compare with the OLS, it is smaller. And when you compare the adjusted R squared, it's higher. Okay. Now I do the same for Lasso. This is the code for Lasso. Take a look at that. For Lasso, Do you see what I have? Do you see what I have? So you have to look into you obtain the metric of evaluation for both training and the test. I will do that for the OLS, okay, training and the test. I will do that for the REACH, training and the test. I will do that for the LASSO, and I'm going to compare across board for you to be able to know which one is the best model. That is the end of statistical story. Is there any question on this? This is going to serve as a very good project for some of you. Where, if you want to enjoy the project or the practical project, why not apply to something maybe in your field where you are majoring in? Somebody have reached out to me about data. Of course, you can use we have data online. If you go to, has anybody visited Kaggle? Can have a lot of data set. We have some data setting out, but do not copy already made research. Does that make sense? Okay, I have a way to figure out. Okay, so but I know you're gonna write a very good project. Before I go today, the bottom line today, to having a recap, I've introduced you to method of regularization that we call LASSO and the REACH. And of course, I also talk about the combination of LASSO and the REACH in the same model that we call elastic net. You know, the essence of the REACH, when you introduce the REACH, of course, it will shrink the regression coefficient corresponding to irrelevant predator towards zero, but not exactly zero. It's still going to retain them in the model. And REACH is very, very good for situation where you want to deal with multicollinearity. Okay, you want to deal with the multicollinearity. Multicollinearity is a problem in regression modeling when the predator variable correlate. When they correlate, it means they are given the same statistical information. But the lasso, on the other hand, if I want to perform variable selection, I actually want to completely eliminate irrelevant variable from my model, then I need lasso. But you know what? Lasso, when variables are correlating, lasso will drop majority of them and only retain one. But by doing that, if they are correlating, your model become unstable. Okay, so lasso is not good, for correlated or variable, but lasso is a very good model for variable selection and at the same time for improve interpretability. If your goal is to explain. I remember I told you the other time we got two major intentions in research. Okay, do you want to explain relationship or you want to predict? The two are not the same. Okay. So, and in a situation where I actually want to retain some variables, even though they are irrelevant. Okay, I still want to relate or retain some, and I also want to get rid of some simultaneously. Then I need two different kind of penalty. So I'm actually going to have a lasso penalty. I'm also going to have a REACH penalty. And situation where you have the combination of the two, we call that elastic net. I'm not going to say where this one is better than that, that is better than that, but I'm actually going to rely on what your ambition or your goal is. But if I don't know your goal, if I don't know what your goal is, and I want to choose the best, then I will use metric of evaluation, okay, that we have. The metric of evaluation, like adjusted R squared, okay, and like root mean square error. Okay, and don't forget, when you are working with the original data set, you have to split your data because you need to split your data, where the majority of the data you're going to train that with the model, Okay, and the small part of the a percentage of the data will be used for testing, to be able to understand the performance. Uh, I have a crucial announcement. Next week, Monday. Uh, okay, okay. Our midterm two is November 24. I think today is 17, right? Which is going to be next Friday. I have one more material to finish. Then on Wednesday is very crucial. Uh, Wednesday, I'm actually just the same way that I did in the when we're preparing for midterm one, I'm also going to do the same. On Wednesday, we're only going to focus on midterm two practice, where I'm going to tell you the areas the midterm two we cover once again. Is there any question for me before I go? It's another weekend. Make sure you stay safe and have a lovely day. Bye for now, everyone. Yeah, November 24.